Okay, so good morning. So we will just continue our analysis of the symmetric top, actually with 1 point fixed, which I mentioned briefly but didn't really emphasize it. And if you remember, we worked out the Lagrange, and there was this I1 prime, which was what I1 plus some mgh square or something like that, right? mh square. So okay, so that was this definition here, and this is the potential energy, and this is what we get. And this is a very nice problem. It is three-dimensional. It has 3 degrees of freedom and 3 constants of motion. So it is integrable. Okay, so we have p psi, which is one constant of motion, p phi, which is another constant of motion. And so you can just see, things to remember is that p phi minus p psi cos theta, you can see, is proportional to phi dot. Okay, so if you want to work out what phi dot is, that's what you will do. Okay, you get that too. So that combination p phi minus p psi cos theta will keep coming. Okay, and we also defined energy, but we subtracted out a boring constant in the sense that omega 3 is something fixed by initial conditions, and that's it. And so for p psi, and so we just subtracted out, and so we got effective one-dimensional problem after we eliminated, theta dot and phi dot using p psi and p phi, and we got this V effective. So this last time I used symbol U, which was confusing, so I switched to V effective. V effective of theta, p phi minus p psi cos theta whole square. That combination you can see divided by 2 I prime sin square theta plus mgh cos theta. Okay, so this is just recap of what we did. Any questions and comments? This is clear, right? No doubts about this. Okay, so now, so what I did was last lecture we switched variables to u equal to cos theta. Okay. You need not do this, but I did that. Okay, and I think so did Goldstein. So g of u, I think this g will differ by some I1 factor. Okay, so it is just 2I1 prime times e minus 2mghu times 1 minus u square minus this thing. So this we saw was a cubic polynomial, and we analyzed the following thing, and I stopped yesterday. For large u, it's true that u belongs to 0 to minus 1 to plus 1. Sorry, it belongs to this interval. But from the viewpoint of looking at the polynomial, we will not worry about these conditions. But this is the physical domain values of u which we are interested in. So g for large u, we saw that what happened was that g of u is greater than 0 because the cubic term, where did it come from? It came from this combination. So okay, so and for small u, it's less than 0. For large, negative u. So it's positive on the other side, but we can also do its computation at u equal to plus or minus 1, and then what you see is that the first term, this whole term drops out because u equal to 1. And this is the minus of some square of something, so g of u is negative. Okay, so that's for u equal to plus or minus 1. So now this actually implies that 1, 0 must always lie about at u greater than 1. Why is that? Because at u equal to plus 1, you can see that it is negative, but for large u it has to go to positive value, so it's a smooth function, so it will have to cross 0 somewhere. Okay. What about the other two roots? There are two possibilities, right? So it's a cubic. So you have a case of two complex roots, whether it's a complex conjugate to each other, or all roots being real. Okay. So let's just consider the case of the two roots being complex. Okay. And mathematically we can prove this, but I tried to prove it and it's too ugly, and so I don't think I'm even going to try to present it. But we'll use physical arguments, which is not mathematically rigorous, but it will give you some insight. It says that you cannot have the other two roots also have to be real. They cannot be complex. Why? Because if that is true, it says for any value of e prime, okay, any value of e prime which we can, and the other constants of motion, it says that there are no turning points. That doesn't sound right. Okay, so so it implies no turning points, and so that should not happen. So the picture should look something like this. Okay, so here we can see quickly, let's see at these 2 points I have drawn something which is negative. Sorry, I did this in advance because if I did it in real time, I'll keep messing up. It took me 2 minutes to do this. Okay, so you can see that it has to, your u1 and u2 are the zeros. So we are interested in the zeros of this g of u. So there are 2 zeros. Okay, of course nothing stops. I mean, this it could be, for instance, we could be in a situation where at u equal to -1 p phi minus p psi is 0. That could happen. Okay, nobody said p psi should be positive or negative. So this quantity could be 0. So this, instead of being negative, it can be. So it could happen that u1 can become -1. Okay, but that will require some fine tuning. But so generically, we'll have 2 turning points, u1 and u2. Okay. Is this clear? Is the argument clear? So the picture will look like this. Okay. It's also interesting to draw V effective of theta now. Now theta lies from 0 to pi. And then what happens here is that you can check at theta equal to 0 and pi. What happens is that coming back to V effective, here it is. Because of the sine squared theta, you can see that, and this is positive quantity, so you can see that the first term will dominate and become very, very large. Okay, irrespective of what mgh cos theta does, this term dominates. So you can see that at theta equal to 0 and pi, V effective goes off to infinity. And then what happens is that a generic curve looks something like this. Okay, and it will have, again, we want zeros of that thing. So this is the value of E, say E prime rather. So when E prime is equal to this, I have drawn this curve for E prime, the horizontal line. It will intersect it at theta 2 and theta 1, not theta 1, theta 2. Why is that? Because u1, I mean, these two theta 1s should be related to those things. So u1 should be cosine theta 1 and u2 should be cosine theta 2. But from this picture, we know that u1, by choice, we defined u1 to be less than u2. So theta, so that implies that theta 2 should be less than theta 1. So you just have to exchange that. Okay. But the interesting thing in this picture we can see is that there is a particular value of E prime, which is E naught, where this is theta naught. So E prime must necessarily be greater than or equal to E naught. This is a condition. Okay, what is E naught? To compute that is a pain, but it's okay. Maybe we will discuss it. But is this clear? So it's also interesting. We can view it as you can start from above and keep reducing E prime. And as you keep reducing E prime, you'll see that theta 1 and theta 2 come close to each other and become one single point. Okay, as you come down. Are these two graphs clear now? Okay, so let us first consider the case. So when E prime is equal to E naught. So it implies that theta is fixed, theta equal to theta naught always, and theta dot is 0. Let's use different color for this. Okay. Then we get this. Okay, so now you can see that what can we say about phi dot? So look at the expression for phi dot. It is p phi minus p psi cosine theta, but theta is fixed to theta naught, so it is p psi cosine theta naught by I1 prime sine square theta. So this is just some constant. Okay, is this clear? Similarly, psi dot is also constant. is also constant. Okay, is this clear? And and you can see that the dependence on, so once you give me theta naught, you can see that p phi and p psi, they all come, I mean, they all work together. And so what happens here is that there is only the top precesses, because psi dot and psi dot and psi dot are constants, and so that implies psi is some, psi is just some constant times t. Okay, so psi is proportional to t, and phi is also proportional. Plus constants will be there, but I shouldn't write it this way. Okay, where beta and beta prime are just some initial values, and alpha prime are these constants. So I'm calling this alpha prime, I'm calling this alpha. Okay, so this is what you will get. Okay, so what happens is that when this happens, the top precesses, okay, rather the axis. So if you look at the top, so if you remember, this is the E3 prime axis, and this was the angle theta. If it is fixed to some theta naught, the only motion that can happen, okay, so this can do this, right? That's all it can do. So conclusion is the top the symmetry axis, that is the E3 axis, precesses such that theta equal to theta naught, and the precession frequency is determined by phi dot or psi dot, but okay, they are related to each other. Is this clear? So this is a very simple case. We have just gotten rid of it, but it's kind of nice. So the property which I mentioned, notation, we will see now. Now we will consider the case when E prime is greater than E naught. Okay. Now we have two turning points. Okay. So what does it say? It says that theta varies, no, theta 1 to theta 2 and back, right? And this is what is happening. Okay. So now there are two situations actually how this will happen. Actually, there's three. One is a limiting case, but we know it also. There are two cases. Okay, depending on how phi dot behaves. Okay, and we look at both of them. First one is phi dot does not change sign as theta goes from theta 1 to theta 2 or theta 2 to theta 1. It doesn't matter. It does not change sign. It is the same sign. Okay, so let's look at phi dot. What was the formula for phi dot? It was p phi minus p psi cosine theta divided by r. some constants, right? So run I1 prime sine square theta. Okay, so the sign is so you can see that this will require, so the numerator is, so denominator is always some positive number. So just let's define let's look at when phi dot. So so if it changes sign, that means it should pass through 0. So that's what should happen. So let's ask when that is 0. Phi dot equal to 0 when cosine theta is equal to p phi by p psi. Okay, and so now you can see that this will require that this and this okay, and theta lies this, let's call this value theta tilde, and theta tilde lies in the range theta 2. Remember theta 2 was less than 0. Is this clear? Only then this can happen. Okay. Is this point clear?
Yes.
Okay, so this is because theta is only varying from theta 1 to theta 2, and if it doesn't happen, if it's not for if it doesn't pass through 0, then it's not going to do that. Then part B, the B is the other case when phi dot changes sign. So okay. Oh, sorry. What did I say here? So when theta tilde does not belong to the range theta 1 to theta 2, okay, phi dot does not change. Is this clear? So I'll draw a picture now before I go. This is what I wrote here, right? Phi dot does not change sign. Okay, so this theta tilde better be outside that range. Okay. So once we have that, so now I can draw a picture of what happens. The same picture I drew last lecture. Okay, so and let's draw one more thing. This is the E3 prime axis. So this guy will be theta 2 is less than theta 1. So this is what happens. And so if you remember that, so theta is in this direction, phi, is phi, and phi goes in these directions. So phi is going to take some particular sign and never changes. Phi dot doesn't change sign. So then it just nicely does this. Let's draw with yellow. Something like this. Okay. So you see notation. I mean, the other one is also notation, but this is what you get. Is this clear? So you can see that there is no phi dot changing sign means you should see something go backwards in this direction. Let's go to case B. Theta tilde belongs to the real, it's in this thing. Implies phi dot changes sign. By the way, even psi dot changes sign, you can think about it. Okay, so it should go through 0 at some point and in this thing. Okay. So now what is the picture I should draw? I should draw something where this trajectory will go backwards. Okay, so let's do this picture again. Same picture like I drew before. So how would we have something like this? So it will, oh, I want to use different color, right? So let's do that. You can see the way I'm tracing it, things are going backwards, right? So you see here, it goes like this. So this, until this point, and then it touches here, it changes. So it, now you see that you're at some point, no, it's somewhere here. It's hard to tell where. Somewhere here in this region, it starts going backwards. Is this clear? Hello?
Yes, sir.
Okay. But it's clear out here that it's going here like this. And if you look here, it is going like this. Okay. And so phi dot, you can see this is the. Okay. So, of course, there is a limiting case. Okay. Which I'll draw only a picture and which is between these two guys. So when yeah, let's say it becomes theta 2 or something. Okay, so let me draw the picture and leave it at that. I'll let you think about that. Okay. Why am I struggling? Yes. Okay, it's not great, but better than everything I did before. So it's something. Okay. So, so question for you is, when does this happen? Okay, so there are. Okay, so are there any questions? Okay, so let us do a little bit more. Try to study where the minimum of the potential. I didn't prove that it will have that nice bell shape, so we just have to take dV effective by d theta and set it to 0. Solve for this. So we can do that. So if we just do that, what we will get is 2 and we have to do the differentiation of the denominator. Wow, a mess. Let's do it. Be brave and do it. cos theta is minus sin square. Sum of 3 input at theta equal to theta naught. Okay, so now we have this weird equation. So let us let beta, we define it to be this combination p phi minus p psi cosine theta. Okay, and then we can rewrite this equation as a quadratic in cosine theta naught theta square minus p phi square sine square theta naught beta plus mgh I1 prime sine theta naught equal to 0. Okay, so this is a quadratic equation. Okay, and of course you can say, but you know, it depends on theta naught, but it also depends on p psi and p phi. Everything depends on all these things, right? But it doesn't matter. You look at this quadratic, and okay, and we expect we need real beta. Okay, so when will that happen? For a quadratic equation to have real roots, what is the condition?
Discriminant should be positive.
Right. So let's look at the discriminant of this equation. So the discriminant is equal to b square. So it's p phi square. Is it p phi square? One second. I think I wrote something wrong there. Now I feel good. Okay, so it is p phi sine square theta naught whole square plus minus 4ac minus 4 cosine theta naught mgh I1 prime sine theta naught will be greater than or equal to 0, or p phi one more mistake. Just once again. I'm just checking my calculation. P psi must be greater than or equal to square root magnitude of P psi. But what was P psi? P psi was I3 recall that P psi was I3 omega 3. So we get a condition that omega 3 must be greater than or equal to something. Okay, please check this, fix this number, fix this quantity, because I don't trust all my calculations here. So I please check these calculations. Okay, check this also. Okay, so what we get is omega 3. We have a constraint that omega 3 uh, has to be, they should be greater than this thing. And what happens when omega 3 is greater than this quantity? That means there exists an energy E prime equal to E naught such that mutation does not occur. There is pure recession with no mutation. Why no mutation? Anybody?
Because when energy is E prime is E naught, like theta dot becomes
Theta becomes
zero.
equal to theta naught. You can
Theta
take
naught,
only one
yes,
value.
theta dot
Okay,
zero.
that is the only thing. Okay, so that's what happens. Okay, so now one more thing is yeah. Yeah, so now I just want to discuss one thing. So I think this sort of concludes. There are more features. However, it shouldn't. However, your study shouldn't end here. To read through the same topic from two sources. Both of them you have to read. Okay. First one is, of course, Holstein. Second one is also interesting. It's Marianne and Thorpe. They don't do exact same things, but please do this. Okay. So I just want to spend the next 10 minutes discussing a slightly different topic, which is the stability of the motion of a rigid body. So right now, for instance, we had we considered two examples. Right, one was the free symmetric object, the no torch acting, and one was the situation where we saw that it was uh, in the presence of gravity. There was a torque. Okay, so we saw two different things. So what we're going to do is we'll consider a rigid body or a torque. I mean, okay. So the first thing is we'll consider free. Okay, and let us choose the body axis to be the principal axis. Okay, and further, let's assume that we have the following inequality, which is okay. So what we'll do now is ask the following question. Suppose, okay, we start with omega equal to some omega 1 E1 hat prime. Okay, that means we're spinning it about the E1 prime axis, and we want to ask, is this stable? Okay, and if you remember, stability is about changing some initial condition and asking what happens. Okay, so what we will do now is we will do that, and we will do it in the following way. We'll look for a different omega, which is, this is exactly fine, omega prime, E1 prime, but now we will add to it lambda E2 prime plus mu E3. Okay, and ask what is the effect. And so the idea is that lambda and mu are, we are going to consider small perturbations, and ask will the motion go far away from what it was. Okay, so that is what we want to ask. What is the effect? Turning on or switching lambda and mu perturbation. Okay, so let's look at the equations of motion which we already had, which was I2 minus I3, if you remember, was omega 2 omega 3, which is lambda mu, minus I1 omega 1 dot equal to 0. Similarly, I3 minus I1 omega 3, which is mu now, and omega 1, which is omega 1, equal minus I1 lambda dot equal to 0. And one second, somebody is asking a question, please ask, or somebody read it out for me.
So in the second equation, that should be I2, right?
I think so. Thank you. Okay, so now the whole point about the lambda and mu is supposed to be small, so lambda times mu is going to be very small, so we throw this term out. Okay, we set it to 0. We are doing only to first order, and omega 1 is constant, so okay, so we are not touching that, so omega 1 dot doesn't change. And now what we want to ask is, does this perturbation, does lambda grow, or this thing? So what we have here now is I3. So we get two equations, which says a coupled equation between lambda and mu, which is this and this. Okay, so we get lambda dot is equal to I3 minus I1 omega 1 by I2 times mu, and mu dot is I1 minus I2 omega 1 by I3 times lambda. Okay, so now we can take this two times, we can differentiate either one of these equations. So let's differentiate the first equation. So we get lambda double dot is equal to I3 minus I1 omega 1 by I2 times I1 minus I2 omega 1 by I3 lambda. Okay, the key point here is that this guy is positive, this guy is negative. Okay, so we can define omega 1 to be I3 minus I1 into I2 minus I1, and we are writing only positive quantities, omega 1 square by I2 I3. Then this is some quantity, this is omega 1 square, which is greater than or equal to 0. So then lambda double dot is equal to minus omega 1 square lambda. You can also check that mu double dot is the same. Okay, so what would you decide? What does that mean? What is it? What is the solution to lambda? First equation. Okay, so now you can see that lambda, once you give it some initial value, it's not going to grow. If you're given some initial value of lambda and mu, so A, I mean, you can determine A and B. So similarly, you can show. I'll let you work it out. So you can see that. Can we? What does this say? Does it mean it is stable or not? Somebody.
So it is not growing, but it is not vanishing either.
Yeah, it doesn't vanish, but if it is small, it remains small. Right, because it's bounded, right? Sine, I mean, it's like lambda will be, A and B are some fixed constants, so lambda will remain some square root of A square plus B square max, bounded by that. You agree?
Yes.
Okay, so it's bounded. So lambda of t remains bounded. That's all. So now let's take another case, okay, where we exchange now. So now what we do is let's do this other possibilities. Okay, so let us do so rotation about omega 2, about E2. Okay, so in this case, what you will get, and we'll do the, what you will get is omega 2 square. Similar thing will go through, and you will get something like this: I1 I2, I3 minus I2, omega 2 square by I1 I2. Okay, and this similarly, if we do rotation about, we'll get similar equations. I'm not saying which is lambda, which is mu. You can figure it out. Then we'll get something like this: omega square equal to I2 minus I3. I'm doing the cyclic thing, so I'm just writing stuff without any. Okay, so now let's look at this. What can we say about this guy? What is the sign of the right hand side here? Still I1 is less than I2 is less than I2. So we can see that this is less than 0. That means omega 2 is pure imaginary. Now what happens to the solutions? If omega 2 is real imaginary, that means these equations will come here like this, or equivalently, if we can make real guys, this will come with a plus sign. So sine and cosine gets replaced by exponential functions, e power plus. And is that clear? So what can you say about this guy? rotation
Now the
about,
solutions lambda will keep increasing.
it can
So
increase,
will
it can
become
be exponential growth, so it's unstable. This is unstable, and this is okay. Is this clear? So we can see that rotation, if you did about omega 1, it is stable. If you do a rotation about omega 3, about E3, it is stable, but the other one is not. Okay. So exercise. Okay. Now suppose we have a symmetric situation, I1 equal to I2, which is less than I3. What happens? This is one situation. The other situation is I1 equal to I2 but is greater than I3. Again, what happens? Okay, so this is the same exercise. You just have to put in. So you will start. I mean, let me just say, for instance, I1 equal to I2. You can see that omega 2 square becomes 0. So what does that mean? That's for you to think. So I think I'm done with today's lecture, and we are done with it's a very rich topic, but I just want to introduce you to the methods. Okay, so I stop here and pause for questions, comments.
Hello, sir.
Yes, Billy.
Sir, I have no doubts from previous lectures.
Yes. Okay. Can you hold it?
Yes.
We'll ask if there is some questions about today's lecture, and then we will move on. I'll stop the recording, and then we can move on to that. Okay? Yeah.
Yes, sir.
Any questions and comments? Okay. So looks like it's been a fantastic lecture. So